Let's turn our attention now to the idea of categorical data analysis. Now, the first technique, they're all based on what's known as a chi-squared. The first technique is going to be goodness of fit. So actually, let's just pretend like that's not there, and let's talk about the learning objectives first, and then come back to that technique. First thing we want to do is, in terms of learning objectives, what we want to get out of all this is identify and understand applications using count data. These next techniques with categorical data is based on count data, how many we observed in specific categories. Want to use the chi-square distribution to compare two distributions, and use the chi-square distribution to determine if a relationship exists between two qualitative variables. So this is the key. To compare the two distributions, this is going to be the goodness of fit test. And determine if the relationship exists between two qualitative variables. This would be a test of independence. So there's two different tests that we're going to actually look at. They're all based on this chi-squared distribution. The CHI is pronounced chi, like a K. And this is the Greek symbol chi. So let's start off with this chi-square goodness of fit. First of all, the data types. We need either nominal or ordinal data. This doesn't make any sense with interval or ratio data because it's count data. The data consists of, again, count data, meaning the data values represent the number of times a specific category was observed. So as an example, if we had a situation where we're looking at the ethnicity of a sample because it's a jury pool selection, something like that. In the community, we may have whites, blacks, Hispanics, Asian, maybe Pacific Islanders, and other, whatever. It doesn't really matter. See, here I have the ethnicity, and ethnicity has 1, 2, 3, 4, 5, 6 different levels in this particular example. Now, if this was a simple case where I had like males and females, see, this is one variable with 2 levels. This we can deal with a straight proportion. But as soon as I go up to 3 or more levels, all of a sudden, what am I going to do with this? And that's what this whole section is actually about. That's what we're going to be working with here. So if I list the number of whites that were observed in the sample, the number of blacks, Hispanics, Asians, so forth that were observed in the sample, I could compare this with the known distribution from census data, perhaps, of how these ethnicities are distributed in the population. So the goodness of fit test will help us decide if the observed data fits this believed distribution. Now this is based on what's known as a multinomial experiment. Remember the binomial? The binomial by 2 had 2 outcomes, and we classified those as being either success or a failure. But you could not classify them as being both. They could only go into one category. It's the same idea on this multinomial. There's multiple possible outcomes, and here 1, 2, 3, 4, 5, 6, and every individual will go into one and only one category. So a multinomial experiment is an experiment which satisfies all of the following. Number one, it consists of n identical and independent trials. So this is the exact same thing we saw in a binomial. N identical independent trials. The outcome of each trial is classified into one and only one of k different categories. Exact same things we saw in the binomial, except for binomial k was 2. Here we would do this for k more than 2. The data consists of count data, the number of observed, in each of the k categories. Well, that was really the same thing as we did a binomial, where the random variable x recorded the number of successes. That was one of the categories. Well, if you had 10 trials, you have 4 successes, the other category had 6. But when you have a multinomial, if I have, go back to that race, if I have 8 whites in this group, I don't know what the rest of them are. I can't say if I have a jury pool of, say, 35. I don't know how the others are distributed. So it's not a binomial situation. It's a natural expansion of the binomial. Now remember, with the binomial, the probability of success plus the probability of failure always had to be equal to 1. Well, here, and also in the binomial, probability of success had to remain reasonably constant for all the trials. Well, it's the exact same thing here, only because there's more than two outcomes. In a binomial, if I fix a probability of success, that also fixes success or failure, because there's only two things that can happen. If there's more than two, if I fix one, that does not fix the others. So I have to fix them all. They all have to reasonably remain constant. And again, just like in the binomial, probability of success plus probability of failure equals 1. Well, here, if I sum up all the pi i's, if I set up all these probabilities for each category, again, that must be equal to 1. So this is the basic idea of what you need for a multinomial experiment. Now, as I said earlier, we will be using the chi-square distribution. That's how we're going to generate or use our test statistic to generate probabilities for a p-value. So let's talk a little bit about some of the properties of a chi-square distribution. The chi-square distribution is actually a family of distributions that's determined by the degrees of freedom. So for the goodness of fit, if I have k categories, then the degrees of freedom would be k minus 1. So if I had 6 categories, then the degrees of freedom would be 6 minus 1 equals 5. Now, just like the F distribution, it's a positive distribution, and because it's a family of curves, depending on the degrees of freedom, the chi-squared could look like this, it could look like this, it could look more like this. It depends on the degrees of freedom. Just like the T distribution changed and the F distribution change with the degrees of freedom, so does the chi-square distribution. And it is a positive distribution. This would be 0. The chi-square distribution can never be negative. Now, the actual test statistic consists of the sum I equals 1 to k, where k is the number of categories, of the, I'm going to say OI minus EI squared divided by EI, where the OI equals the observed in group I, where I would be 1, 2, 3, 4, all the way up to 6 if k happened to be 6. EI is the expected values. And the expected value simply equals n. This is the total number. This is the total number of observations. Oops, that's supposed to be total. Multiplied by the probability of being in individually each of the specific categories. And we're going to work this out and show you here in just a few moments what that would turn out to be. Now, the assumptions for the chi-squared test is that number one, the experiment satisfies the properties of the multinomial. All of the expected values, these guys that you would calculate, are at least 1, and no more than 20% are less than 5. And you need to address each and every one of those. So let's jump into an example now of that goodness of fit test. So here's an example. A random sample of students on a community college campus was selected as part of a survey process. Those conducting the survey wanted to determine if the sample was representative of the various ethnicities on campus. Based on the published data, the true proportion for each ethnicity was obtained. Does it seem reasonable to believe that the sample was ethnically representative of the campus? So, based on what was available, these true proportions, these pi i's, there were 35% that were white on this particular campus, 12% black, 31% Hispanic, 5% Asian, 13% Pacific Islanders, and 4% others. Now, when I add these all up, what I get is n equals 170. So notice if I go through each of these of the assumptions for the multinomial experiment, that they're all going to be satisfied. There are 170 independent and identical. Well, independent meaning through the sampling process wherever we used, the assumption there is that if the first person I happen to pick happened to be Asian, that has nothing to do with who I pick next. It's just some type of random process. So they're independent, and it's identical because I'm using the same random process. Now, each individual falls into one and only one category. Somebody is not going to say that they're both white and other. They're going to pick one. Now, obviously, there's a mixture of different races. But if you look at like any college entry form where they have your ethnicities, you pick one that you most identify yourself with, so that's not a problem. Now this is clearly count data. It's how many individuals were observed in each of those groups. So everything's reasonably satisfied for the multinomial experiment. If I add all these up, the probability, this is going to be 1. So what's the expected value? If I take 0.35 and I multiply it by 170, I will get 59.5. If I take 0.12, multiply it by 170, I get 20.4. So it's saying 12% of this should be 20.4. That's how many blacks I should have gotten. I should have gotten 59.5 whites, and so forth. And if I keep doing this, the Hispanics would be 52.7. This would give me 8.5, 22.1, and 6.8. This is how many expect to see. And obviously, you're not going to see 0.5 or 0.4 of a person. But based on these probabilities, in the long term, that this is the number that you expect to see. So what this test statistic does is it's going to take the observed value, this 53. Here's my OIs, O1, O2, O3, O4, so forth. And here's my EIs, E1, E2, E3. That's where I'm going to subtract, square, and divide by the EIs. Remember it said the test statistic was the sum of the OIs minus the EIs squared divided by EI. That's exactly, these are the values. Here's the OIs. Here's the EIs. Now, the assumptions here are, number one, the experiment satisfies the properties of multinomial experiment. We already did that. All expected values are at least 1. Here's the expected values, and they are, in fact, at least 1. Because they are at least 1, we don't have to worry about this last one where, well, actually, I take that back. We do need to look at this. No more than 20% could be less than 5. And I look at this, my smallest is 6.8, so I don't have to worry about this. So now I need to think about calculating this test statistic. Well, doing this, here it is, I wrote it out again. I would take the observed, which, let me scoot this down just a little bit. There. The observed is going to be 53 minus the expected 59.5. Square it and divide it by 59.5. And then add it to the observed 27 minus 20.4. Square it, divide it by 20.4. And keep right on going. Now, here's what's going on. Let me draw a quick curve, and let's just say that our chi-square distribution happened to look like this. Okay, here's 0. As what I observed differs from the expected, if I subtract those and square it, I'm always going to have something positive. This is going to contribute to the test statistic. So I'm going to start coming out here. This is going to be my value of chi-squared down here. So if these are all very, very, very close to each other, when I subtract and square and add all these up, I'm going to have a small value of chi-squared. A small value of chi-squared is associated with a large p-value. So we start thinking in terms of null and alternative hypothesis. All right? If you have a large p-value and a hypothesis test, you would fail to reject. On the other hand, if these differences were big, it's going to contribute more and more to this test statistic, and I'm going to be out here with a value. So the farther and farther out here I get a smaller and smaller p-value. Large differences, small p-value, we would reject. So that should give you some kind of hint what the null alternative hypothesis is going to be. The null hypothesis would be, in this case, pi 1 is equal to, we said 0.35. Whoops, that's supposed to be a pi. Pi 2 equals 0.12. Pi 3 equals So that was 0.31. Pi 4 equals 0.05. And let's see, we had pi 5 equals 0.13. And pi 6 equals 0.04. In other words, these true proportions that we got from the census or wherever it is that we actually got them from, we're saying here that these are correct. We're saying these are correct. And what we're looking for is evidence that these aren't correct. In other words, what we observed did not match the expected. So the alternative hypothesis, much like an ANOVA, would be that at least one of the pi i's is not equal. Somebody's different in here. So once I calculate this test statistic and find this p-value, I can go ahead and actually complete the hypothesis test and come to a conclusion. Now, fortunately, we will be using TC stats, so we won't have to do all that by hand. So to do a goodness of fit test with TC stats, what you really need to do is set up two different columns. One column will contain the observed data, which here I simply named observed. You could say ethnicity or whatever. You can make it more meaningful. And then another one contains the probabilities, which again I just simply called probabilities. Now, what we're going to do here is select categorical and the chi-squared goodness of fit. And you see here I have the observed counts and the probabilities. So I want to tap on what I want for the observed first. So I'll tap on observed. And then tap on probabilities. See, one of the things it does, TC Stats does, it lists your null alternative hypothesis for you, and it adds these up. Now, there's a certain tolerance built in. If these add up to like 0.0001, it's going to tell you that. Then you can make a decision as to, hey, you know, it was just rounding error. It's not that big of a deal because I had to divide two numbers to get these probabilities. So it didn't work out exactly perfect because of rounding, but it's no big deal. If this gets beyond a certain tolerance level, it's going to be red. It's going to really alert you that there's a problem with one of your assumptions here regarding the sums of the probabilities being equal to 1. Now, if by chance you had it in the wrong order, all you got to do is tap on switch order, and it switches around and makes a probability observed and now the observed probabilities. Clearly, when these added up, 170, that's a lot bigger than 1. So it's alerting you there's a huge problem there. Again, if I tap switch order, it'll put it back in the right order. Now, we also need the expected values, and we're kind of almost doing this backwards. When you do a hypothesis test of goodness of fit, and actually also a test of independence, which we're coming up to, on TC stats, during the process of the hypothesis test, it will actually give you the information you need for your assumptions. So here was the information you needed regarding the sum of the probabilities equal to 1. If I tap update, see, all of my expected values show up down here. So I don't have to calculate any of these by hand. Remember, I went through this process and found all these by hand so you understand where it's coming from. But TC Stats does it for you, so you can now take a look at these and address the assumptions. For my students, you need to make sure when you address your assumptions, this matrix here, all these values, all these expected values must be written down. I have to see your expected values. Now, if I wanted to save them, I could simply tap here on Save Expected Values. Now, you see here, it has a default name, Observed Expected. Well, Observed Expected, that sounds like a contradiction. Well, all it does is it's saying the observed counts, because I call this observed. If I call this ethnicity instead, it would say ethnicity expected. So it's going to take the name of the, whatever you name the column with the observed, and then append to it the word expected, so you can save it, and it's going to create a new column in TC Stats that saves these if you need to save it. That's like totally up to you. Remember the 6 categories, degrees of freedom was k minus 1, 6 minus 1 was 5. And here's the p-value, 0.0058. So based on this p-value, we would reject the null hypothesis, and we would then obviously conclude that somebody is different, that this does not fit, this racial or ethnicity distribution from the sample does not statistically fit the actual population. Now, from here, we're not going to try to figure out which groups are different. We're not going to do some type of multi-comparison sort of thing like we did with ANOVA. You simply go say, hey, it fits or it doesn't, and then stop there.